In any mathematical figure presented to you, say a pyramid, you know this is length, this is width or breadth, and this one is height. You know that, right? Yeah, so what my point is, most of us grew up being taught by an evil teacher that length, width, and height are the 3 dimensions, and that's it. But no, here comes the fractals. You may not know it, but fractals are like the air you breathe, all around you, endless. They have irregular shapes that just can't stop repeating themselves. It's as if they're manifesting it more, and more. But it would be a whole other story if my money manifestation also works.
I need that money, I really do. I need that money.
We just need money.
Maybe Jesus is giving me side-eye right now, but I'll figure it out. Maybe. Anyways, it was mathematician Benoit Mandelbrot who first created this term fractal in 1975. And according to him, all fractals show a degree of self-similarity. This means that as you look closer and closer into the details of a fractal, you can see a replica of the whole. A fern is a classic example to spirit my words. Look at the entire leaflet. See the branches coming out from the main stem? Each of those branches is like a mini-me of the entire frond. A perfect photocopy, I'd say. After all, nature did it, unlike those human printers. Still messing with my documents. So like this, fractals keep multiplying as we zoom further. Now, fractals can also be created through a feedback loop, which is called iteration, where the results of one iteration form the input value of the next. Don't trouble your brain, see this Nautilus shell. If you look at the interior of a shell, you'll see that each chamber of the shell is basically a carbon copy of the preceding chamber, just smaller. This also reflects their space-filling nature. Space-filling in a sense, as you zoom into a fractal, like here the spiral pattern of the shell, you continue to see that pattern filling the space at all levels of magnification. Is there any place where the pattern is not there? You won't find any. So this was all about the fractal having a self-similarity property. But they are also recursive, regardless of scale. Whenever you go into a store's dressing room and find yourself surrounded by mirrors for better or worse, you're looking at an infinitely recursive image of yourself. I told you they are everywhere, you're just not realizing it. Okay, let's not make this spooky like Donald Trump creeped out Taylor Swift. Maybe he was also using the fractal by repeating the word beautiful 5 times in a sentence about Swiftie.
What do you think about Taylor Swift?
Yeah, I think she's beautiful. Beautiful.
Anyway, let Trump be Trump. What I was saying is fractals are a paradox amazingly simple, yet infinitely complex. One of the earliest applications of fractals came about well before the use of the term. Louis Fry Richardson was an English mathematician in the early 20th century studying the length of the English coastline. I bet you've never thought about measuring a coastline, and if you did, you'd probably end up being the one to introduce the use of fractals, don't you think? But right now it's Fry Richardson who reasoned that the distance of a coastline depends on the length of the measurement tool. Always an approximate number. Let's see the British coastline for example. If you ask how long is the coast of Britain, the answer is the same, the fractal rule. That depends on how closely you look at it or how long your measuring stick is. Suppose if you measure the coastline by taking a map and placing a ruler around the edge, you can get a certain value for the perimeter, say 11,073 miles. But if you were to walk around the beaches of Britain and add up all your steps, you'd arrive at a very different but way larger perimeter, which would rise to 19,491 miles. But that value is also an approximation. To get a more accurate value, you'd have to measure the length of every boulder, rock, pebble, and even every grain of sand. And at a microscopic level, sand is a fractal as well and cannot be easily measured. So the long answer is, the coastline gets longer and longer as you measure it more closely, and it approaches infinity, which is also called the Coastline Paradox. Now, carrying the same paradox further but put forward by Helge von Koch and the Koch snowflake. Ever noticed the shape of actual snowflakes rather than using it as a slang term? I still wonder why overly sensitive people are called snowflakes. Or maybe I'm too old for this Gen Z generation. Anyway, what I know is that snowflakes also show fractals. This fractal involves taking a triangle and turning the central third of each segment into a triangular bump in a way that makes the fractal symmetric. You'll notice that each bump is of course longer than the original segment, yet still contains the finite space within. You can show this by enclosing it in a finite circle or any other shape, but its perimeter is infinitely wiggly. You think of mountains and other objects in the real world as having 3 dimensions. In Euclidean geometry, we assign values to an object's length, height, and width, and we calculate attributes like area, volume, and circumference based on those values. But most objects aren't uniform. Mountains, for example, have jagged edges. Hikers know this better, as the surface is rough and nothing like those smooth geometric shapes. Let's understand this through animation. Loren Carpenter realized he could use the fractal process to give any desired level of complexity to the images in his animations. You see how 100 mountains turn into millions as it zooms in? Believe it or not, fractal process is a game changer in the animation industry. Before the advent of this process, animations were somewhat flat and incredibly laborious. But now the level of animation is insanely incredible. All the shapes that come out of fractal geometry look like nature. This is an amazing fact that is hard to ignore. There are no perfect circles and no perfect squares in nature, and when you look at trees or mountains or river systems, they don't resemble any shapes that are used in math. But man, fractal geometry does this with ease. Most of you have heard of this irregular shape for the first time, but let me tell you, it's older than dirt. You'll find them in cloud formations, tree limbs, stalks of broccoli, and even in the rhythm of the human heart. It's even believed by some that the universe itself may be a fractal. Are you ready to zoom in from here? As you zoom in, you discover the universe is made up of billions of galaxies. Inside those galaxies, you would find trillions of stars, billions of solar systems, and planets. On one of those planets, we have our Earth, where you would find multiple continents, cities, and humans. Inside a human, you would find a brain made of millions of cells with trillions of synapses firing away. Inside those cells, you would find DNA. Inside DNA, you would find atoms, electrons, protons, neutrons. Deeper still, you find quarks, neutrinos, and so on. Maybe continuously deeper than a human brain cannot even think of. You can also create fractals with mathematical equations and algorithms. Some start with a basic line segment or structure and add to it. That's how you make a dragon curve. Man, I've literally tried this curve 100 times, but I messed up every single one. Comment below if you nailed it and, of course, the trick you used. I'm damn sure by the third or fourth iteration, you'll begin to realize why fractal geometry wasn't developed before the computer age. So this is the fractal paradox. It is recurring, it is self-similar, and it is infinite, like that infinite ways you could press that juicy subscribe button.